join. I hope the screen is visible to everyone. So today we will discuss this. Wait, I think someone is trying to join. It should be automatically added, but it's not working, I think. Hi, Shitra Mohan. I just
Uh,
started.
yeah.
Yeah,
Good afternoon, sir.
good afternoon. Okay, so I will probably discuss what sir is going to discuss in the lectures because the questions will be closely related to that in your tutorial. So I will go step by step, and if you have any doubts, you can ask in between.
Yeah.
Yeah. This is tutorial 3. So in your lecture number, I would suggest which one is that? Is this? Yeah, in lecture number 11, if you see that in your course, I will start with that. And so what he is trying to do in your lecture 11 is just some finite difference method, for solving PDEs. Okay. So what method he is trying to cover? Let's see how to discretize. Okay. So I just go with. So one thing he mentions is like you can discretize del phi over del x as something like this. Pi I divided by del x at what should I say, at xi basically. So how do you do that? So that you have already seen using Taylor series expansion. So how? So you can write phi at x plus h. So what is phi x plus h? Which is phi x plus h phi prime x plus h square by 2 phi double prime x and so on, right? So if I start at phi x, then phi x plus h will be your phi value at succeeding step x plus h and so on. So okay. So how do you use phi dash x? So I just write phi x plus h minus approximated as phi x plus h times phi prime x, and other parts are omitted because it's just a approximation. So I just write phi dash x is approximated as phi x plus h, just phi x plus h minus phi x. So it's just a simple way of the same thing turning. Yeah. So you approximated your derivative in this way. This is the ordinary, but if you want to consider partial derivative, then it's just so phi del phi over del x is approximated as phi x plus h minus phi x over h. Okay. And in this case, if you consider if your x is like, okay, I discretize x step, right? So discretize x. How? So space is if your x is belonging from 0 to 2, you discretize like this: 0, h, 2h, and till 2. Okay. So h can be your 1 as well, depending on that. So you do have that many steps, but h is small. So like, so you can consider 0, 0.1, 0.2 up to 2. Okay, like this. So your del phi over del x at, so if you want to calculate at 0.2, so del phi over del x at 0.2, x is equal to, then it is basically phi at 0.2 plus h minus phi 0.2 divided by h. Okay, and h is just 0.1 here. Here it is 0.1. So you can easily find out this value. And in general, he's talking about at xi. So xi is what? So here xi is basically your, if you have starting point, say 0. So if you say x naught, this one is x1, this one is x2. So xi is ih basically. I would say. So if you want to calculate at xi, that means this implies that del phi over del x at x is equal to xi, which is same as phi xi plus h minus phi xi divided by h. And you know what is xi, which is same as phi I plus 1h minus phi ih divided by h. I think it's well clear now, like how do you get it into that? So I would suggest, okay, just add another paragraph, similar way. Okay. So you can easily do like, so try to find approximation del phi over del x can be approximated as phi x minus phi x minus h divided by h, or del phi over del x at x at I can be approximated as phi I minus phi I minus 1 divided by h. H is basically your Daleks. So I just, why does it look like this? So Daleks is H. Okay. So can you do that in a similar way? I think you can write in the same way. How do you do that? So what do you do in this? You try to try writing Taylor series expansion again. So how do you write now? So phi x minus h. So instead of phi x plus h, I write phi x minus h, which is phi x minus h phi prime x plus h square by 2 phi double prime x and so on. So I can neglect this term and find phi prime x to be same as phi x minus h divided by h, and that's the same. So it's easy. Like, how do you get it? Next thing is discussed about finding a higher order approximation. So if you want to find out like a central difference, say. So for central difference, you do have a different approximation. So why it is called as it is called as backward difference. Because you are going backward in time or space. And here it's called as forward in space because you are going in forward direction, x plus h, right? And for central difference, you do have forward and backward. So it's like forward and backward together. Yeah, so here you do have, yeah, so in that way you can find out. So I would suggest you to find an approximation of del 2 phi over del x square using Taylor series. Can you do that? Just try for 5 minutes. I think it's easy. Okay, so if you have tried it, so I will go with. So how do you do that? So I just use phi x plus h, which is same as phi x plus h times phi prime x plus h square by 2 phi double dash x and so on. So I don't need to go further because this thing comes over here. So I neglect these things. I have phi x, I have phi x minus h, which is phi x minus h times phi prime x plus h square by 2. Oh, so one thing I would suggest is, okay, right. I want to cancel something. Okay, so how does it go like? So I just add first equation and third equation together, and second equation I subtract. Maybe I like to this. Okay, so phi x plus h, I add phi x minus h. It works like this, and I subtract 2 phi x. So what does it give now? So phi x plus h is phi of x plus h phi prime of x plus h squared by 2 phi double prime x. So if you subtract it, if you add both of these things together, then it will be 2 times phi of x, right? 2 times phi of x. And this thing and this thing together got cancelled. So we have h square phi double dash x and minus 2 phi x. So that will also be cancelled. So you just have h square phi double prime x, right? So what does it mean? It means phi double prime x can be approximated as phi x plus h minus 2 phi x plus phi x minus h divided h square. So it's kind of central difference approximation, right? Why it's central difference? Because we are considering x plus h, x minus h, and x all together. So that's central difference. And or equivalently, I just write as phi double prime. So if you want to use partial derivatives, so I just write like this. Del 2 phi over del x square, and x is equal to xi, which is say approximated as phi of xi plus h, so xi plus 1 minus 2 phi xi plus phi xi minus 1 divided by h x del x square. Okay, so this is kind of approximation you can achieve. So the questions may come on this in a similar way where you need to find approximations. For third order derivative, it can be second order, more precise, more points. First order derivative in just a different way. So questions will be based on that like this. Okay. So I just go with another thing that he's mentioning is, so how do you approximate now? How to approximate PDs, right? Okay, so I start with heat equation in a similar way that is given by this. So how do we approximate this? So which scheme would be good? So he's mentioning about forward in time and backward in space. Okay, so that is called as, oh sorry, central in space. So that is called as FTCS scheme, right? So how do you approximate using FTCS? So what does it mean by forward in time? So I just discretize. There is a grid. Okay, I just make it big. Okay, let me make a big grid. So you have the values. You have on one side you have x, on one side you have t, and on other side you do have some solution. You have uxt. Okay. So how do you approximate grid x naught, x1, x2, and so on, xn? And on another side you have something t naught, t1, t2, t3, and so on, right? So that is your grid. And on these points you have x1, t1, x2, t2, like this, and so on. Okay. So what does it mean by forward in time? So I want to approximate del phi over del t at t equals to tn. So basically, I want to approximate, I just write, what is the approximate value ut uxt at x is equal to xn, twice like this, xn, and t is equal to tn. Okay, right. So what is the approximation? What is the approximation value of this at x is equal to xn and t is equal to tn? Maybe, okay, it's not like this. So at x is equal to xi. So I have different discretization. X equal del x is different and del t. So this is the difference is del x, delta x, and another difference is delta t. So that's here. So we do have difference between delta x and delta t. These two things are different, and hence the number of points on the x space domain and number of points in the time domain are different. Okay, depending on delta t and delta x. Right. So how do we find the approximation? So I just write the PD in this way: del phi over del t at t is equal to tn. So we do have tn and alpha del 2 phi over del x square at t is equal to tn. So on both sides, you should have t is equal to tn, x is equal to xi, right? So we need to take both things all together, right, to describe this. Okay, so what is del phi over del t? That is, you have already studied the approximation, so I just write phi x. So phi xi and tn plus 1, right? Forward in time. So I just go forward direction and xi tn divided by delta t. Okay. And on another side, we do have alpha and del 2 phi over del x square. How do you find out the approximation that we have already discussed? That is phi I just write phi xi plus 1 comma tn minus phi 2 times phi of xi tn plus phi of xi minus 1 tn divided by del x square and so on. Okay, so what does it look like? So yeah, I just give a short form to it. So that is, so it is phi xi. I can write s space domain letter in the subscript and capital N in the superscript. So capital N plus 1. So this is phi I n divided by delta t. And that is same as alpha times phi of xi plus 1 tn. That is phi n, phi I plus 1 n. That's just a shorter notation to write. Divided by delta x square. Okay. All right. And so that's all. And you find, so how do you find out the values of from this? So how do you find out? So if you want to calculate phi I n plus 1, then it is just alpha times delta t and this thing. So I just write like this and plus phi I n. So what does it do? What does it do? So it calculates the value of phi xi tn plus 1 based on the point. So what points it is taking? So if it is like this, xi minus 1 and xi plus 1, then you do have points ti. So this is xi, and you have to calculate at, so here you have tn plus 1, tn plus 2. So to calculate at this, you need this value and this value, right? And this value as well. So these three values will give you these points. And similarly, to calculate this value, you need this, like this. So it's kind of triangulation and so on. So to cover this line again, so just try to write a numerical code to solve this. You can write this, right? Just try to write a numerical code. Okay, so that's what he covers in lecture 11. And maybe the questions based on that. So you can try doing, I just give you one question based on that. Let me see. Yes. Extend to you. Okay. Okay. So can you write a numerical scheme? Solve this equation del u over del t same as del u over del x using forwarding time and backward in space. Just try to solve it. And how do you do that? You can use initial condition, something fx, right? Find out this. Okay, just try to write this. Okay. Okay, if you have tried it, just simple, right? I just add one more page. Okay, how do you solve it? So you do have, so del u over del t can be just approximated as un plus 1. Oh, I just typed in subscript. That is just ui n plus 1 minus ui n divided by delta t. Okay, so that's for what? And w over del x can be approximated as ui n minus ui minus 1n. That's the back part, right? So in total, what's the, just using bit bytes like this. Okay, so in total, if you substitute over here, then it is just uin plus 1 minus uin over delta t, same as uin minus ui minus 1n. And then you can find out what is un plus uin plus 1 and so on. So if you have initial condition ux0 equals to f of x, it means that t naught, so ux naught t naught is f of x naught. Okay, so if you have to find the value at u of x naught at t1, then what should it be? Why does u at x naught at t1? It should be what value? Okay, so I just show it in the diagram like this. So at x naught, so it is starts from x naught, x1, x2. So this is x, this is t over here, t naught, t1, t2, and so on. So to find out the value at x naught, t1, you need the value at this, and you need the value at this, and you need something in the previous direction, but you don't have anything there. So better you describe the initial conditions at the boundary. So the question will have boundary initial conditions. And if you go over here, then you can find out using these initially. If you go over there, you can find out using this and so on. So the problem is at the boundary, right? So we need boundary conditions. Okay. That you should keep in mind when dealing with the initial conditions. Why does it look like this? Okay. So I just go with another lecture 12. Does it show? Okay, so they talk about two types of stability analysis. Let's discuss. One is stability analysis. Two types they discuss von Neumann and another one they discuss is convective. What does it say? Okay, so what do you mean by stability of a numerical solution of a PD, right? Okay, what is stability? How do you define stability? Let's see. Okay, so stability is like, so if you have small errors, like, so if you have exact solution and you have numerical solution, then this is called as error. And if this error becomes very large, then your numerical method will become stable, unstable. So error becomes large, then unstable. So we want error to be less. We want error to go towards zero some way, so that your method will be stable in that case. So we need to find the values in the coefficient such that it leads to a stable solution. So how errors propagate used through the numerical scheme, these things it will tell. Okay, we will see an example and see how what's the stability we will looking at. Okay, so you do have, so we have already discussed this, and this PD, if you remember the heat equation, it is this phi in plus 1 minus phi in delta T, same as plus phi n minus, so that is n just phi n del x square. So what is the error? So if I say that numerical solution at in is ni, so I just use the same notation. So okay, so what is the numerical solution? That is ni, capital N. Oh, they take a small n here, so I just write small n. Small n, small n, small n, small n, small n. So that is the numerical solution, capital N, and DIN is the exact solution. And this is your error. Okay, this is your error at x and t. So that is called as pointwise error. Point error. So we just finding the error at phi x and t, an exact solution at phi x and t. Okay, so if you look at the how the error is growing, basically how error is growing, right? So just consider EIN plus 1 minus EIN delta t. So we just try to check in time direction. Okay. So if you subtract it over here, that is Ni minus Ti, whatever, then you do get the similar type of equation, which is alpha epsilon I m plus 1 epsilon I n plus epsilon I minus 1 n divided by del x square, right? And then you check like, so for stability, you just consider that your error at n plus 1 should be less than error at n, right? So this thing is very needed for stability. of course, you expect your error to be less after some time from the previous time as compared to the previous time. Okay. And then how do you set up a condition over it? That depends on like how do you do that? Okay, so if you go in your lecture, they do something to set up a condition such that, yeah, so they came up with something like this expression to be 1 plus alpha delta t by del x square, and then say that this thing should be less than 1. It implies something over there. So they came up with some condition which says that del t by del x square should be less than 1. Means that del t is less than equal to, sorry, alpha del t is less than half. Okay. So that's called as von Neumann criteria. Right. So for this type of equation, del u over del t is equal to alpha del 2u over del x square. You do have, if you have such condition like this is happening, then you say that your numerical scheme is stable for this kind of equation, right? But if you change this equation to somewhat like for this is for FTCS scheme. But if you have a different scheme, like I would say,
Excuse me.
yeah, yeah.
Yeah, actually, I just missed the point. Actually, the small n and capital N. Earlier, we were using capital N for like
Yeah, yeah,
changing
yeah,
up, marching up time. We changed to
yeah.
small n. And exactly what is this? Miss, in this, when you are writing heat equation, the next line onwards, I am not able to follow. Will you repeat just
Which one?
how this n after this phi I to the power n plus 1, this small n and this capital N, what is the difference?
This capital N is actually the numerical solution. So yeah, explain. Wait.
Okay, and that's why we have changed it.
Yeah, it's
Okay,
sorry,
then
it's just numeric, phi numerical.
okay, and di we are using for the notation is for
Phi exact is di.
or exact. Okay, sir, please continue.
And that makes the error actually. So get this. You will get this condition, but this condition is very specific to your numerical scheme. So in questions, maybe you will have a different numerical scheme or even the different equation, right? And then they will ask like, what is the criteria for stability? Then you do have to do the same thing. You have to write like this in error terms and try to get an estimate like this and similarly. Yeah. Okay. So that is von Neumann criteria for this specific scheme and specific PD. And then there is another type of equation which is called as convective equation. I'm not going into much detail. Convective equation. For this, they do have this type of PD. And this is they're using backward scheme for solving this and forward. So what is the condition in this case? In this case, you do have a different condition. We have to check it, I think. Which one is that? Why is that? Okay. Okay, so in this case, you do have condition u del t over delta x is less than 1. So you just try to check how this is coming. But in this way, in this one, they have set up a different type of strategy to do, but I would suggest you to go by this method in this case as well and see what is happening. Yeah. Okay. All right. I just go with another series. Okay, so what is method of I just want to mention one thing. It's these types of schemes that you have studied or seen, these kind of explicit schemes. Okay. What are explicit? So if I just give you a simple example of an OD. So if you have an OD like this, du over dx is equal to fxy, or what should I say? Fx basically. So if you discretize this OD, then you have ui plus 1 minus ui equal to h times fxi, or ui plus 1 is ui plus h times fxi. So this scheme is explicit. Why? Why it is explicit? Because the solution value is dependent on the previous 10 steps. So if you see the solution at xi plus 1, so u xi plus 1 is basically dependent only on previous values of u. But implicit is different, right? Implicit is what? So if I have here, if I take, okay, let me see. Okay, suppose there is a scheme like this, and you do have something like ui square, ui plus ui plus 1 minus ui minus 1. So this ui is dependent on previous values. You cannot dissolve it some way. So if the dependency is on the previous and future values, then, or it is just not the previous values, then of course it's implicit. So you will find it somewhere. Okay. Um, I will go with a method, different method of lines or such. Okay. So it is like this. Okay. So method of lines. So we start with a similar PD, same as alpha del to t over del x square. And you do have a discretization in this way, which is t I n plus 1, which is same as t I n plus lambda times ti plus 1 n minus 2 ti n plus ti minus 1 n. And lambda is alpha delta t over del x square. So that we have already derived before. And we describe something, the initial conditions at something like this. Tx0 is equal to 0 degree. So if it is the temperature, And okay, I just don't write these values. That's just mathematics. Tx0 to be 0 and alpha to be your 0.835, lambda to be something like 0.028075 or whatever, delta t to be 0.1, and what is delta x? Delta x is 2, and t0 t to be 100, and t100 t to be 50. So what are these? That are called as boundary conditions. These are called as the boundary conditions. Okay. So how do you apply the discretized equation? So you do have, okay, I think just trying to solve it. So here, if you have I to be 1 and n to be 0, okay, then you have t1 1, which is same as t10 plus lambda times t20 minus 2t10 plus t00. If you substitute it over here, then you find this value. What is t11? Okay. So you got the value of t11, which is dependent on again t10, t20, t10, and t00. So here, if I write the diagram, so t00 is here. Wait, t10, t00, t20, and on next line you have t11, t21, t01. So that is dependent on these three that I've already mentioned before. And t21 is dependent on t30. If you have to find this, then you need these three values, right? So it's just an expansion in this way. And so I was just worrying about boundaries in this case. So what is the boundary? I equals 0 and I is equal to 5. Okay. Okay, you don't need to describe it. Yeah, because it's already described what is the values at these points and what is the values at these points, like this. Okay. So similarly, like it's just an illustration, like in this lecture, they just illustrated like how to find these that I've already mentioned, T11, T21, and so on. And if you have to go above, so this line is the initial condition for illustration purpose. This line is just the initial condition, T naught, T1 naught, T2 naught, and so on. This line is the next line of the solution. This line is the boundaries, initial boundary conditions, whatever is the ending point. You find these values over here. That is the first time, and then second time with all the points like this. So you need these 3 points, these 3 points, and all for other three points, these 3 points, and all you find out like this. So that's called as method of lines, basically the same way. Find out. Okay. Um, so what about the implicit scheme? So they also mentioned about implicit scheme. How do you find out in this case? So you can also do that in that way as well. So I just write one implicit scheme. So if you have something like this, in implicit scheme, how do you find out the solution? So what is del 2t by del x square? If I want to make it implicit, then I just write like this: ti plus 1 at n plus 1 minus 2 ti n 9 plus ti minus 1 n plus 1. So I just write n plus 1 over everything. So I want to calculate at n plus 1 and I, basically. N plus 1, tn plus 1, and x. Okay. So, and del t over del t can be approximated like this way, which is n plus 1 tn plus 1 xi, which is just t n plus 1 I minus tin divided by del t. So what is this? This is backward difference, backward in time. And this is already central difference that we have seen before. So the overall scheme will be BTCS in this case, backward in time and central in space. So BTCS is a implicit scheme, right? Okay, so if you apply this and you come up with certain equations. Okay, let me write. So I just write in this manner. So write like this: minus tin, capital N, is same as lambda times ti plus 1 n plus 1 minus 2 lambda plus 1 ti n plus 1 plus lambda ti minus 1 n plus 1. So here it's becoming implicit because I is dependent on I plus 1, I, and I minus 1. Okay, so it's kind of an implicit scheme. So how do you find it? So the triangle rule doesn't work here. Triangle. Okay. How do you solve it now? So you need, so T1 n plus 1, T2 n plus 1, T3 n plus 1. These are unknowns. Yes. And you do have given, so basically if you have, if you plot this, so Ti at n plus 1, basically Ti plus 1, n plus 1, and Ti minus, sorry, it is Ti minus 1, Ti plus 1. And Tin is here. So Tin is here. So you can find out Tin using these three. Okay. So it's going, the triangle is going in the backward direction in this case, right? This is tricky, right? How to find out? So in this case, you need initial conditions, but from other side, then you can find out instead of 0, you can have the initial condition at x is equal to 1, something like that, right? Yeah. Maybe if there is another way to find out. Okay. Yeah. Okay. So implicit schemes are a bit difficult in that sense, and you have to find out these values in this way. Okay. So you have to use some sort of boundary conditions as well in this case. Find the value. Okay. Yeah. So I will go with another sort of lecture. Okay, so we will try to solve this equation now. So can you solve it using your approach? Like, how do you solve it? Try to solve the previous equation implicitly. Just give 5 minutes and try to solve it using these values that is mentioned here using an implicit scheme like BTCSMs. Try to solve it. So the idea behind is straightforward, but it's with a little twist. Okay. So in this case is a little twist. So why is the little twist here? Because of the implicit scheme. Why does it look like this? Why? I blank page I left, I think. Okay, so I just start with n equals to 0, I is equal to 1. Then in that case, what is the value? You will get something like T2, T1, and T0. So I just write something like, okay, I just write A11 T21 plus A12 T11 plus A13 T01, which is same as minus something minus T10 minus T10. So that is the boundary condition, right? And that's value is they have given to be, I think this value is 0 or something like that. Okay. Okay, this is just 0. So but the main idea is I'm just telling. Okay, so if I is 2, then what is the equation? N is 0 still. You have A12 T31 plus A1 A21. I just write second row second column. T21 plus A23 T2 T11, which is same as what is this? T2 minus T. Okay, so I is 2 minus I T to 0. So that is again your boundary condition, right? So you know this value. Okay, so T11, T21, and T31, right? And similarly, you have T41, something here, T41 plus something here, T31 plus something here, T21 to be 0. That is the boundary condition. We take it 0 and so on, so forth. So you end up having a matrix which is like capital AX is equal to B, where A is your tridiagonal matrix. So if I write here like this, so if I write here like this, T11, T21, T31, and so on, Tn1, Ti1 basically, and so on. And this is your B matrix, this is your A matrix, whatever multiplied to it. Okay, these coefficients and all. So you end up having a tridiagonal matrix. What does a tridiagonal matrix means? You do have entries over here, over there, over there, and that's all 0. Okay, so you do have these 3 entries and that's all 0. That is called as tridiagonal matrix. And how do you solve it? You can solve it easily using some algorithms that are available to you. So one algorithm is Thomas algorithm that Sir has mentioned already in his lectures. So you can solve it using that. I'm not going to detail of this algorithm, but you can do that. Oops. And then you can find out these values T1 and T11 up to Tn1, right? So for the implicit systems, it's like this. You need to find out these coefficients. So just verify that, like whether your scheme is explicit or implicit. If it is implicit, it is hard. You need to find out the solutions using matrix. In the matrix form, you need to solve them. They are not directly available to you very easily. But if you have explicit numerical scheme, then they are available to you very easily. That's also, I think I covered most of the parts today. Did you understand everything, Kshetra Mohan? And if you have any problems, you can ask. Just give some time for asking some questions.
Hello.
Yes, Kshetra Mohan. Yeah.
Thank you very much, sir. Actually, it was a very good session. I could know a lot within less time. In fact, this time I could not like cover all these lectures previously. It will be very nice. I mean, next time when I meet, it will be, and it can be more interactive if I go
Yeah,
through and I have some doubts and I can ask.
so that would be
Okay.
very good.
So
Good.
I took a lot of time when you were ending because somehow my headset was not working. So
Okay.
I struggled for 2 3 minutes and finally got it. Thank you very much. I really means I had done earlier. I had known little about these things, but I have never utilized. I'm thinking of after like refreshing all these things. I will try to utilize it in writing like this numerical schemes, all these things,
Yeah.
and
So I
to do
think
some
the
numerical
next lecture
problem.
will be on dynamical systems.
Yes, sir. Okay, thank you very much again for your very it means your high level of patience. And so when only when one
Yes.
person is there still. Okay, thank you very much. We'll meet again in the next time. Will it be weekly?
Yeah,
Just
yeah,
doubt.
it's happening from the last 2 weeks, and it's
Yeah,
yeah.
yeah. Somehow by this I got very
Is it your
serious.
first time joining this session?
Yes, this is the first time I'm joining, and I will continue. I
Okay.
will continue, but this time I could not like
Is
participate
this time
very.
nice?
Sorry, sir.
Is this time fine for you? 6 p.m. 6
This
p.m.
time is fine. This time is very fine. Six
Okay.
o'clock we don't have anything. Okay. See you, sir.
Yeah.
Thank you very much.